zeros of a polynomial. Now, to find the zeros of a polynomial may be better served by first deciding what a polynomial actually is. So, to explain that, I may be better off telling you what a polynomial isn't first, and then whatever left is what the polynomial will be. So, these are things that are not polynomials. Y equals x to the negative 1 plus y equals, or plus x squared. This is not a polynomial. Why? Because x is raised to the negative exponent. You can't have negative exponents and still be a polynomial. Exponents have to be variables. I'm sorry, exponents to the variables have to be whole numbers, as in 1, 2, 3, 4, 5, 6, 7, 8, or 0, but it can't be negative numbers. Y equals the square root of x also isn't a polynomial, mainly because y equals square root of x is the same thing as x raised to the 1/2. You don't really know that yet, maybe, but you definitely cover it in this class if you don't already know that. But because that's a fractional exponent and it's not a whole number, the square root of x is not a polynomial. What makes this last one not a polynomial is you have a variable that exists in the denominator. Whenever you have a variable that exists in the denominator, it's no longer a polynomial. It's actually a rational equation. The graph is completely different from what a polynomial graph looks like. A rational equation generally looks something more like this. Maybe with the slant asymptote and something else. And lots of other ways, but rational equation is definitely not a polynomial. Some other functions that are not polynomials are absolute value functions, trig functions, logarithms. None of these functions are polynomials. So they all exist in the world of not a polynomial. What a polynomial is an equation such as y equals x to the 5th plus x to the 3rd plus x to the 2nd plus 1, and so forth, where all the variables are whole numbers. So you want to write that as a definition? I would. What is a polynomial? An equation where all the variables, all the exponents to the variables are whole numbers. At some point you may want to write all that down as a note. I'm about to erase the screen. The degree of a polynomial is equal to the highest exponent of the polynomial. So basically what that means is this. Given the polynomial y equals x to the 5th plus 3x squared plus 2x plus 9x to the 13th plus 24. You have 1, 2, 3, 4, 5 terms in this polynomial, and you got lots of different coefficients. You got 1, 3, 2, 9, 24. But its degree is its highest exponent. So you look 5, 2, this exponent is understood 1, this exponent is 13, and this doesn't have a variable. So technically its exponent, its degree is 0. So the degree of this polynomial is 13 degree. 13. But technically, each one of these terms have a degree. This first term is to the 5th power, so it has degree 5. This next term is to the 2nd power, so we say it has degree 2. You may also say this is the quadratic term. This exponent, the next one has a degree of understood 1. So we say it has degree 1. Or you may say degree of 1. You can also call this term, because it has degree 1, the linear term. Linear means that if you graph just that piece of the function, that piece will graph as a line with a slope of 2. So that's the linear term, it graphs as a line. This piece has degree 13, and it dictates the degree of the entire function because it's the largest one. So if the whole function does what it says, it doesn't do linear things, it doesn't do quadratic things, it doesn't do things that x to the 5th power does. It does things that the 13 tells it to do. And this last term is a constant term. You already know what a constant term is, and it has degree 0. 0. Someone might ask, well, why does it have a degree of 0? Well, if you ask that, I want to tell you that. The reason why it has a degree of 0 is understood x to the 0 power next to that 24. The reason why is understood x to the 0 power next to that 24 because x to the 0 power, or anything to the 0 power, is equivalent to 1. Meaning that that's really 24 times x to the 0 power, or 24 times 1, which is still 24. And that's the reason why this polynomial has degree 0. There's a little understood x there to the 0 power next to it. Pretty nice thing to know. But keep in mind, you're going to be asked questions along the lines of, what is the degree of this polynomial? And your answer is, has a degree of 13. You should get all that as a note as well. Another thing about the degree is it tells you some stuff about the polynomial. The degree tells you the maximum number of zeros a polynomial has. So you focus on quadratics, things like y equals to x to the square subtract 1. And you know the zeros in that quadratic will be the places that it crosses the x-axis. So if that's the case, you have a 0 here and here. So you see you have 2 zeros. So it tells you the maximum amount of number of zeros a polynomial has. Because technically, some polynomials won't have the same number. They may have less than that. For example, I give you y equals x squared. But that graph looks like this. A little polynomial that sits down right there on the origin. It only has 1 0. So you can't have more than its degree, but you can have less than its degree. And that's more zeros, that is. You can't have more zeros than its degree. And for that matter, I could give you y equals x to the squared plus 1. And that graph is this one, where it meets there at positive 1. And this graph doesn't have any zeros at all, because it never actually crosses the x-axis. So it has no zeros. So again, our degree says it can have at most 2, but it may not have any at all. The general shape of a polynomial. There's 2 ways we describe the general shape of a polynomial. We describe it by its end behavior. That's talking about what happens as one end goes to the left and one end goes to the right. We also describe it by its number of terms. Those are all the max and mins, all those hills and valleys that graph actually has. A linear equation, y equals x to the first. It has degree 1. So that tells me some things about the graph. What that tells me is this. We know linear equations look like this. This graph never changes direction. It goes up and up forever. If you start at this point and you go to the right, you just go up. You never start to change direction and go back down. The reason why is because it's linear, and this graph should have 0 terms. The number of terms is determined by the degree subtract 1. So since it's determined by the degree subtract 1, and my degree is 1, my number of terms should be 0. It's a quadratic equation. We know the degree is 2. And it should have 1 term. Because my degree is 2, I subtract 1 from it. It should turn once. So this graph actually changes directions. On one end it goes one direction, on another end it goes another direction. And both of those directions is up. So since we said we determine the general shape of polynomial by its number of terms and its number of terms and its end behavior, let's talk about the end behavior. As this function goes to the left. All right, so degree 3. Cubic equation definitely has degree 3 and should have 2 terms. On the left side, the cubic equation goes downward, comes back up, turns down again, goes back up again. If we actually try to count the terms, you can see this. we got a turn happening here, we got a turn happening there. After that, it goes up forever and never comes back down. On the left, it goes down forever and it never comes back up. So this has two turns. This has one turn, this has 0 turns. So that's just 3 of them. We can keep going on forever, right? So we're going to eventually see a general shape happening as we go from even, as we go from odd and even degrees. We can eventually see that some things kind of happen similar to all of those, or similar in all of those. Y equals x to the 4th power, we say is quartic. And that's basically a type of quadratic equation, essentially. And if we think about it, how many terms should it have? You may be saying 3. So it actually goes down, comes back up, goes down, comes back up again. So we actually count off those terms. Each either has 1, 2, 3 terms. And it should. You may also notice this one has 4 zeros. 1, 2, 3, 4 places across the axis. Being to the 4th power, that would be the most amount of times you could cross the axis, right? Quintic is the name of a polynomial. It's x to the 5th power. This has a degree 5. And it has to have 4 terms in it. It has degree 5. I know my term that's is 1 less than a degree. So if I thought about it, went down, this is 1 term. Go down again, that's 2 terms. Turn up again, you got 1, 2, 3, and you turn one more time. So check it out, make sure I did it properly. You should count 1, 2, 3, 4 turns. That's the general shape of them. Basically, after seeing 5 of those, yeah, I'd have a pretty good idea what the general shape of those graphs are. Let's put them all together. We're going to talk about the end behavior. So in this function, you have 2 ends. As this is the x-axis, this is the y-axis. As x approaches the left, or we say negative infinity, the function y approaches, it goes downward. So x goes to the left, the graph goes downward. It's going down further and further. So we say y approaches negative infinity. As x approaches the right, this is positive infinity. That little kickstand is a part of the script for infinity. It's just an old way of writing it, and that's the way it's written by mathematicians. But as x goes to the right, this is going toward positive infinity for x. The y value goes upward, so the graph is constantly growing. So the y value approaches positive infinity. So x approaches there, y approaches positive infinity. And the next function, in the quadratic term, you're going to notice they both go in the same direction. So what you will notice is the even exponents generally go in the same direction. Either they both go upwards or they both go downward. But the odd degrees have opposite ends. One goes down, one goes up. So that's the one characteristic that you can use to dictate any graph, any polynomial. So if we look at this, as x goes to the left towards negative infinity, the function shoots upward. So x approaches negative infinity, y approaches positive infinity. And as x goes to the right towards positive infinity, y still goes up. So as x approaches positive infinity, y also approaches arrow. The arrow means approaches positive infinity. Oh, that is so ugly. Okay, so if you think you understand it, pause the video and answer the next 3. I'm going to fill in the answers for the next 3 in about 5 seconds. So pause the video and go and answer the next 3. So that's essentially it. You should have had this: x approaches negative infinity, the function approaches negative infinity. So x approaches positive infinity, function approaches positive infinity. So we didn't actually get to zeros of the polynomial, but don't worry, we will tomorrow. Good luck with homework.